Good morning, everyone. My name is Bahram Khan, and today I will be presenting on thermal management in 5G and advanced communication semiconductor systems. Our advisors are Dr. Noordin Sharifi and Dr. Navid Asadi. This presentation focuses on how advanced communication systems face new challenges with heat and how engineers solve them using innovative materials, designs, and simulations. Here's an overview of what we'll cover today. We'll start with an introduction to why thermal design is crucial for 5G. Then, we'll discuss unique thermal issues in advanced communications, followed by high frequency device behavior, RF front end modules, and the thermal effects on signal integrity. Next, we'll move into design constraints, materials, TIMs, PCB level solutions, and active cooling methods. Finally, we'll explore thermal modeling, co-packaged systems, and two case studies before wrapping up with our summary and outlook. As 5G and beyond technologies push for faster and more compact semiconductor devices, heat management becomes one of the biggest design hurdles. Unlike traditional electronics, RF and wave systems handle high-frequency signals that generate intense heat in very small spaces. Without proper thermal control, performance drops drastically and reliability suffers. In other words, thermal design isn't just about keeping things cool. It's about enabling high-frequency performance safely and efficiently. 5G systems operate at millimeter wave frequencies, meaning shorter wavelengths and smaller components. That leads to higher power density, more energy in smaller volumes. At these speeds, switching events happens millions of times per second, and every transition produces heat. Moreover, smaller packages have less surface area to dissipate it. These thermal challenges affect not just performance, but also regulatory compliance, since overheating can violate emission or safety standards. At high frequencies, semiconductor devices experience rapid voltage and current changes, leading to transient power losses. Cores, mixers, and signal processors create localized hotspots. Materials like gallium nitride and silicon germanium generate significantly more heat per square millimeter than standard silicon. On top of that, the skin effect, where current crowds at the surface and substrate heating both increase with frequency, amplifying thermal stress. Now, let's talk about the main heat producers. RF front-end modules and power amplifiers. Power amplifiers handle high signal gain, but that also means high power loss as heat. Designers must balance linearity, efficiency, and thermal safety, a tricky trade-off. Co-packaging digital and RF components raise local temperatures even more. If not managed, the heat causes signal distortion and output degradation, limiting overall communication quality. Temperature directly affects carrier mobility, gain, and phase stability of semiconductors. As the temperature rises, so does the thermal noise floor, which lowers the signal to noise ratio. This leads to data errors, timing shifts, and distortion in the RF chain. In addition, thermal drift can change impedance matching, reducing power transfer efficiency. Essentially, as the system gets hotter, signal quality and integrity suffer exponentially. One of the hardest challenges is space limitation. Compact RF modules and smartphones leave almost no room for airflow or heat spreaders. Metal shielding, while good for signal isolation, can trap heat inside. Modern packaging like LGA, UFN, and flip chip makes it difficult to attach traditional cooling methods. All these factors force engineers to innovate, using better materials and more efficient layouts to balance performance and temperature. In high frequency electronics, the right material selection is critical. For example, gallium nitride and silicon germanium are preferred for their performance, but require materials like aluminum nitride or beryllium oxide for heat dissipation and electrical insulation. Packaging often uses thermally enhanced epoxy mold compounds to help transfer heat without losing signal performance. Engineers must carefully design material stackups to ensure both electrical and thermal optimization. Thermal interface materials, or TIMs, play a huge role between the chip and heat spreader. They must be thin, uniform, and applied precisely to avoid interfering with signal paths. In RF systems, even a small air gap can affect both thermal flow and RF shielding. That's why TIMs with a low loss tangent and high conductivity are ideal. Designers often co-optimize TIM placement with shielding and grounding to improve both cooling and signal integrity. Beyond the chip, the printed circuit board (PCB) also contributes to thermal management. RF boards use ground planes and thermal via directly beneath high power components like PAs and LNAs. Materials like Rogers or Isola laminates combine high glass transition temperatures with low dielectric loss. The number of layers and their stack-up design determine how efficiently heat can move away from hotspots while maintaining signal performance. Infrastructure like small cells and base stations can't rely on passive cooling alone. They incorporate heat sinks, fans, and heat pipes to handle the continuous power load. Outdoor enclosures need to withstand extreme conditions while keeping internal electronics stable. In core network systems, liquid cooling is becoming more common for managing high density FPGAs and amplifiers. Active cooling ensures long term reliability of 5G equipment, especially in dense urban deployments. Simulation tools are essential to predict heat behavior before physical testing. Engineers use multi-physics modeling that combines electromagnetic, thermal, and structural analysis. Finite element analysis (FEA) helps trace internal heat flow, while computational fluid dynamics (CFD) evaluates airflow around the system. This reduces costly trial and error during prototyping. Because 5G devices often operate in burst modes, transient heating must also be modeled accurately. As RF and digital components merge into the same package, new thermal bottlenecks emerge. For instance, FPGAs and ADCs and power amplifiers all have different temperature profiles, yet share the same cooling path. A single shared heatsink must manage uneven heat distribution. This trend toward co-packaged architectures pushes designers to adopt localized cooling, like micro heat spreaders or vapor chambers, to maintain consistent performance. Let's look at two examples. Case study 1, a gallium nitride based 5G power amplifier reached junction temperatures over 100 degrees Celsius. By using a copper molybdenum base and AIN substrate, along with a vapor chamber and fine heat sink, engineers reduced the temperature by 28 degrees Celsius. Case study 2, a millimeter wave transceiver inside a 5G handset used a graphite sheet spreader and PCB ground via to lower thermal rise by 30% during uplink transmission. These real-world examples show how combining materials and layout design can drastically enhance performance. To summarize, 5G and beyond introduce unprecedented thermal challenges due to higher frequencies, tighter packaging, and greater power density. Managing heat is no longer an afterthought, it's part of the design from day one. Future systems will increasingly rely on integrated cooling within the chip package, smarter materials, and co design approaches that merge electrical and thermal engineering. Thank you for your attention and watching.